everyone. Welcome to the first webinar of AI and Big Data in Finance in 2023. We are super happy to have two amazing researchers with us today. Jann Spiess from Stanford GSP is going to talk about unpacking the black box regulating algorithmic decision. And then Paul Goldsmith-Pinkham from Yale is going to discuss him. And then that is gonna be followed by a Q&A from participants. So Jann will have 30 minutes to do his presentation, followed by 20 minutes of discussion by Paul, and then 10 minutes of Q&A by the audience. These three parts are gonna be recorded. And then that would be followed by a 15-minute unrecorded open discussion in which all audience will be upgraded to panelists so that we can actively discuss things together. So to all the audience, please post your questions on the Q&A function of the Zoom throughout Jann's talk. In the middle of the talk, about minute 15, if there are clarifying questions, I'm gonna in the Q&A, I'm gonna stop Jann and ask him these questions. And then the rest of the questions will be, I'm gonna call on you at the end of the webinar in the Q&A session to ask the questions yourself. So without taking any more time, Jann, the floor is yours.
Thank you so much for having me. Thanks a lot, Paul, for doing the discussion today. So I'm very excited to present work with Laura Blattner, who's at Stanford GSP, and Scott Nelson from Chicago Booth on unpacking the black box, regulating algorithmic decisions. So our work is motivated by the increased use of prediction algorithms in high-stakes screening decisions, such in medical testing, hiring, and lending. And the starting point of our analysis is noting that in many of these decisions where we use algorithms in order to support decisions, there could be incentive conflicts between the agents building such algorithms and principals overseeing it. So to be very concrete, let's consider the case of medical testing, where maybe an insurance company, who would be the principal in that case, worries that a hospital that builds an algorithm in order to perform decisions of who to test may have an incentive to overtest. So their preferences over the use of that algorithm may be different from that of the insurance. Or in hiring, there may be an employer who cares about the diversity of their workforce and may be concerned about the fairness of a screening tool that is used by a hiring manager to decide who should get interviewed. Or finally, and this will be the main example that I will use during my talk today, in lending, there may be a bank who decides who to give credit to using an algorithm, but a financial regulator who may worry about the disparate impact of these decisions or about model risk that those decisions imply, and therefore has an incentive to regulate. And that's exactly what, of course, is done by regulators in the financial market. And so in that context, the fact that many of those decisions are now taken by algorithms rather than by human decision makers in principle has a big advantage, because these algorithms may allow us for a more systematic, even ex ante review of the properties of these decisions if those decisions are taken automatically by algorithms rather than, say, by a loan officer. But at the same time, our ability to do so is complicated by the complexity of the algorithms that are used, which has led to a call for simplicity and transparency of these algorithms in order to be able to regulate them well. And so what we study in this project is we build a principal agent model that effectively represents those trade-offs that we face when we think about regulating complex models, and that specifically asks how we can effectively mitigate incentive conflicts when the algorithms that are used to take decisions are so complex that they cannot be fully described, and we then apply that model to the case of credit data. And just to give a quick preview of the main ideas to expect in my short talk today. So the starting point is that the complexity of algorithms means that an agent cannot fully describe the algorithm to the principal. So relative to a standard approach to regulation, we basically assume that the information that can be provided about the algorithm that's used here, about the rule that is used to give credit, isn't complete. It's not going to be able to completely describe what's going on because the algorithm is too complex for that. And then we discussed two options in which we could deal with that. A first option would be that we limit the agent to a simple or transparent algorithm that is so simple that it can again be fully described, meaning we constrain how complex the algorithm can be that is used to assign credit. Or there could be a second policy option. The second policy option would be that we instead require the maker of the algorithm to provide some simple description. So we're not necessarily ex ante constraining the complexity. We allow the algorithm to be very complex, but instead we rely on a simple description of that complex algorithm that is an imperfect representation of what's going on, and, for example, expresses the algorithm in terms of a few key drivers. And we then use that for effective regulation. And tools for that are generally available. So when we think of these complex algorithms being, for example, neural network, even in those cases, there are nice technical tools available that provide explanation of those complex algorithms. However, the usual way in which those explanations are motivated and the usual way in which those explanations are constructed doesn't really have any economic justification of what it means to explain something well, but instead is based on mathematical axioms that then allow us for technical implementation. And so what we do in kind of deviation from that existing literature on explanation here is basically trying to understand the role of explanation of complex machine learning models in a context of a principal agent model where that explanation is not an end in itself, but instead a means to effective regulation. So what will be my main takeaways that I will show in an example today and that we develop in theory in our paper? So first of all, in our theory, we make precise and justify explanations of complex machine learning models in a principal agent model where explainability is not an end in itself, but a means to effective regulation. And we argue that in many cases, simply restricting functions ex ante to very simple functions that are straightforward to regulate may have too high of a cost in terms of the efficiency loss of making those functions too simple. But that oversight based on a simpler representation can help to mitigate the cost of reducing complexity while also mitigating the cost of preference misalignment. But that the design of the way that these explanations are constructed, that their design matters for results, and specifically that we should use ways of explaining complex algorithms that are targeted towards a specific application that the regulator here cares about. We then empirically demonstrate that those results matter in two substantial applications to credit underwriting that I will show today, where we basically calibrate our model to the data and then show that these trade-offs work out, at least in these empirical examples, in a way where it would be too costly to rely on very simple algorithms and where we can do better by using an explanation that is targeted to the specific use case. And then finally, practically relate this to a broader agenda where, together with FinTech Lab, which is a DC-based think tank, we evaluate how well diagnostic tools that are already available out there address regulatory requirements. And while this is not part of this current project, I'm just flagging this in case any of you are interested in kind of the more applied and practical side of this work. So we relate to a large number of literatures here because this work really tries to tie together a few literatures, specifically on the one side, a law and economics literature on fairness and discrimination and oversight of algorithms, together with a literature that analyzes data analysis when there are conflicts of interest in the background, and of course, a finance literature on disclosure and supervision that all have become, in our eyes, particularly relevant to the question of how to regulate machine learning and AI systems that are typically studied by the computer science literature. In order to approach that, we are relying on ideas and tools for mechanism design and specifically optimal delegation in order to make progress on modeling as well as providing solutions. So here is a quick overview over the talk I will give for the next 20 minutes. So first of all, I will sketch our theoretical model, but then focus on a specific example to make the main points that we develop more broadly in a paper. I will then go into an empirical implementation of that model where I specifically consider two regulatory concerns when it comes to lending, specifically model risk management and disparate impact. And I will then discuss a few relationships to the existing literature and conclude. All right, so let me first set up our main model. So as I said, we are concerned with the interaction of an agent. We assume that that agent chooses a prediction function, so a mapping from some covariates x to some number, in order to maximize their utility, and a principal who may have a different utility from the agent. And in order to make this more concrete, okay, so let me first get up the general setup and then get you the specific application to a lender. Okay, so our assumption here is that the principal can choose some restrictions on what the agent can do. So here we assume that those restrictions are given by a subset of all the mappings that the agent can choose based on whatever prior information the principal has available. The agent then chooses a function from that delegation set based on a signal that that agent receives about the distribution of the data. So that we think of kind of using training data in order to decide on a good prediction function using some, say, machine learning algorithm. And so far, of course, this is a very standard delegation model. So a principal choosing a restriction, an agent choosing a function subject to the restriction. So what's the main deviation here that we use in order to model the case of complex machine learning models? So the main deviation from standard theory that we use is we assume that when the principal chooses a restriction, then the principal cannot fully observe the complex functions that are potentially used by the agent. So the agent maybe uses some very complex relationship between covariates in the data and the outcome, say a neural network. The agent cannot fully describe that to the principal, so the principal cannot really put restrictions on that full function, but instead can only put restrictions on a simple explanation. And an explanation here, we basically think of a projection of this very complex function into a simpler space that, for example, describes the first order behavior. So think of this as a simpler model that describes the behavior of the more complex relationship between covariates and outcome. And so that may, for example, represent a proxy model. So I only present you a simple linear model that describes the complex relationship. Or it may be I'm giving you only the most important variables in that function and how they relate to the outcome. Or it may be that I can only evaluate the complex model at a few data points, and I only give to the principal information about how that function behaves on those few data points. And so in this model, we are then asking, what are the right policy choices by the principal? And specifically, we assume that the principal has two possible policy options that will go into more detail in an example in a moment. We assume the principal could either restrict ex ante the agent to only using simple functions that are so simple that I can fully describe them, so that that problem of not being fully able to observe the function goes away, or leave the ex ante functions unrestricted, meaning I let the agent choose any function, but then I choose a simple explanation based on which I make my regulation decisions. And so in order to make this somewhat more tractable here, I'm basically assuming that there is no difference in information between the principal and the agent. So relative to a standard delegation model where we usually think that there's some private information, I was going to assume that principal and agent here have the same signal about the data, so that I can focus only on that challenge that arises because the choice that is made by the agent cannot be fully understood by the principal, in the sense that we can't fully describe this complex function, but only a simple description of it. All right, so that's our main setup. Let me now make this much more concrete and show you in a concrete example what we mean here, so that this is easier to follow. So I started with an agent. The agent chooses a prediction function. The principal then has some different utility from the agent. Here, let me make this more concrete. Let me just say the agent here is a lender. The lender wants to choose a credit score. The credit score is a function that uses information in a credit file, which I call X, and then determines the probability of some Y occurring, where Y is the probability is in this case repayment. So effectively, what the lender does here is using information in a credit file in order to predict somebody's probability of repayment. We could assume different utilities here. For convenience, we could just assume that we want to evaluate a credit score by the mean squared error relative to repayment. Or we could also explicitly model the benefit that the lender has from having a better or worse credit score by saying the lender gets a certain benefit if they give out a loan and the loan gets repaid. So say they get a profit of R in that case, or they face a certain cost C in case that they give out a loan, meaning that the credit score is above a certain critical threshold, if that loan doesn't get repaid. The choice is then overseen by a regulator. That regulator also has a utility over choices by the lender. However, that regulator's utility may be different from the lenders. And so let me give you 3 concrete examples that are motivated by practical considerations that exist in regulating lending models. So a first example would be that maybe the lender and the regulator have different risk preferences. So here I'm modeling this in a very simple way. I'm assuming that the lender just cares about expected utility over all states of the world, while the regulator cares specifically about expected utility in the low state of the world, where the economy may be in a low state. So this models the idea that maybe the lender doesn't really internalize issues that arise when the economy is specifically in a bad state, in which case the regulator may be worried about contagion or systemic risk in the economy, while the regulator really wants to make sure that even in a bad state of the economy, the lender doesn't go under. A second example could be that the lender and the regulator care about different target populations. So maybe the lender cares about their profit when giving out loans to a typical applicant based on their historic consumer base, while maybe the regulator cares specifically about credit scoring that works well for new customers that are not traditionally part of the consumer base of the lender. And then so this case, for example, we could model that by assuming that the regulator in this case cares specifically about utility conditional on some distribution of consumers or customers. And then finally, we may care about disparate impact, meaning that the lender just cares about having a credit score that fits well, but maybe the regulator also cares about distributional considerations. For example, the regulator may care about the credit score not being systematically different between a majority group and a minority group, and may attach a penalty in this case to utility if the majority credit score, which here is represented by the G=1 group, is systematically higher than the minority credit score, which here would be the G=0 group. Okay, so what I will do in the example here to make this concrete, I'm just going to choose for convenience the case where we evaluate our credit score simply by mean squared error. So we want to come up with a credit score that models as well as possible the relationship of repayment and the X covariates in terms of mean squared error. And I'm going to consider this example of a risk preference where the regulator cares about the performance of the credit score in a low state of the economy, while the lender cares about an average state. So going back to our original model, so what was the model here? So we started with the rule setting stage where the regulators set some rules of the game, which I will come back to in a moment. We then assume that the lender here observes information about the data. And so let me make this very concrete. I'm assuming here that there are only 2 variables in the world. Those 2 variables are both binary. The variables are, has that person who applies for a credit defaulted in the past? And the second is, has this applicant have a home equity line of credit? I'm going to go back in a moment to why I chose this particular example here. And I'm assuming that there is a linear relationship between those with a fully interactive model. So that's not really restrictive. That relationship, because there are only 2 binary variables, basically describes any complex relationship between the X covariates and my repayment. And so the idea here is that this kind of represents this complex relationship that we may not be able to fully understand because it's too complex. Of course, here these are just 2 variables, but I'm doing that just to make the point, make this transparent. And specifically, I'm assuming here that this relationship can depend on the state of the economy. So specifically, the intercept and the effect of the home equity line of credit here may depend on whether the economy is in a good state or a bad state. So the idea here is that if the economy is in a good state, then the overall probability of repayment is higher. So that's the intercept. And then the effect of the home equity of line of credit may also be different. So the idea here is that home equity line of credit, we see as this example here, not an empirical statement, but this is just for the sake of this example, as something that may be seen as a positive signal about your ability to repay a loan if the economy is in a good state, because having a home equity line of credit means that you have some collateral. But in a bad state of the economy, that may actually be a problem because you may already have a mortgage on your house, and that may mean that in a bad state of the economy, you're actually already under financial pressure. So we see home equity line of credit as a potential variable in our data that may have different implications for your ability to repay, depending on whether the economy is in a high state or in a low state. We then assume that the lender learns this relationship and chooses some credit score that is effectively a function that maps those x's to some evaluation of somebody's probability of repayment, and subject to some restrictions that the regulator sets on these functions that can be chosen by the lender. And then finally, we assume that utilities are realized. And here, for simplicity, as I said, I'm just going to assume that this is mean squared error. Okay, so in this game, I now want to consider different ways in which the regulator could set restrictions for the choice by the lender. So importantly, these restrictions will be subject to the following information constraint, which is that the regulator cannot process the fully complex relationship between the X covariates and repayment, or that the lender does not reveal that full relationship, but instead that the lender here only reports a simple projection, or that the regulator can only have access to a simple projection of that complex function. Let me be very concrete here. So because the lender here can only see the simple projection, I'm considering here basically two different options for that. So I'm assuming that the fully complex function is basically this fully interactive linear regression, but that's too complex for the regulator to understand. So the regulator only understands a simple projection onto either the first covariate x1 or the second covariate x2. So the first option here being represented in the middle and the second option being represented on the right. So either the regulator looks at the world only by projecting everything onto x1 or to x2, but the full function that projects on both would not be available because it's too complex for the regulator to understand. So that's kind of the way in which we implement here this idea that there's a very complex true function or a very complex function that the lender chooses and only a simple explanation. Okay, so I'm now going to just give a quick preview of the main results in this example, and then I will show how this plays out in our empirical example in the last few minutes of my talk. So I'm assuming here that there's this relationship between repayment and between those different variables. I normalize everything here so that the math goes to in a simple way. And I'm assuming that the lender cares about overall mean squared error, and the principal or the regulator here cares about mean squared error in the low state of the economy. And in that case, that means that what the lender would optimally choose is the lender would love to choose the coefficients that represent average behavior. So they want to choose those values for the coefficients that represent the intercept and the effect of the home equity of line of credit that represents average behavior. But a regulator would really prefer to use those coefficients that represent worst case behavior in a low state of the economy, while both agree on the effect on past default and the interaction term here. So this now allows us to model what happens in a first case that we can consider, which is the case where the lender just can do whatever they want and the regulator lets them do things without any restrictions. So in that case, the lender would simply would choose their first best, which would lead to a maximal distortion, in the sense that the credit score would be exactly what the lender prefers and would not reflect the preferences of the regulator. A second case that the regulator could use is the regulator could ex ante restrict the lender to functions that are so simple that they can be fully explained. So say the regulator forces the lender to use a function that only uses the covariate x1. And in this case, we would end up with a simple function that is aligned subject to that constraint. So the intercept that is used is now the intercept preferred by the regulator, but that strips out any effect of the other variable x2 or the interaction. So it eliminates misalignment, but at a large cost. And so here's already the main slide that I want to convey today. So we could instead assume that the regulator now relies on a simple explanation of the complex function in order to restrict the choices by the lender. And we first start with an agnostic explainer, where we choose that variable to minimize the information loss. So where that variable that we choose in order to explain the variable preserves as much information as possible around the original function. And my example here is chosen in a way where that would be variable x1. So in that case, I would restrict the choices by the lender in a way that is expressed by the projection onto x1, which in this case would align the choice of the intercept. It would also still align the interaction and the choice of the effect of x1 because we aligned over those. But it would not get rid of the misalignment around the function x2 because to the regulator, the effect of x2 is now not visible. We could instead have chosen an explainer that is more specific to the source of misalignment. So the source of misalignment here is different risk preferences specifically playing out in the function x2 and the intercept. So if instead I had chosen a description of the complex function that was more targeted to my source of misalignment here, which in this case is variable x2, had I chosen that instead, then I would have gotten a first best in the sense that the choices would have been fully aligned between the lender and the regulator, because in this case, focusing on the projection with respect to x1 means that as the regulator, I can't really see what the lender does with variable x1, but that's not a problem because we aligned about that choice. Instead, I'm focusing exactly on those parts of the function that are misaligned. Okay, so what's the takeaway is, of course, this was a very simple stylized example where we modeled kind of a very complex model, like usually we'll think of maybe a neural network as a simple function that was, as just a linear regression function on two variables and their interactions. And then we modeled simple explanations by these simple projections. But the general takeaway here is that basically, at least in this simple example here, if you're using ex-ante function restrictions that limit function complexity, we may have excess cost in terms of restricting the efficiency of credit scoring. If we use explainers that minimize the information loss, meaning they describe the overall behavior by the function in terms of variables that show first-order behavior, then that may help us, but may not be as good as using explanations that are specifically targeted to the source of misalignment. And we considered here risk preferences, but of course, something similar would have gone through if, for example, I had focused on disparate impact, so on different preferences around fairness. And so let me now just show you how this plays out in data. And I'm just going to take 5 more minutes to wrap this up and show you how this plays out in the empirical example we have here. So I'm just going to use exactly the same example. I'm going to implement it in some credit bureau data. So the lender here wants to minimize mean squared error, and the regulator wants to minimize mean squared error specifically in a bad state of the economy. And so in this case, we use a large credit bureau data set with a subsample of 400,000 people in our credit data set, where we have credit file data available as well as repayment of personal loans. But notably, we have many applicants that have missing outcome data because they were never approved for a loan. And so what we're doing now, we are leveraging this in our simple model in order to be able to vary the outcomes in good and bad states of the world. So effectively, what we're doing in this simple example here, we assume that applicants that have missing data will default in the low state of the economy while we pay back in high state. So it's a very extreme way in which we can model that, but just to get some clarity of how this would work out empirically. So basically, in a good state of the world, which we assume is in 80% of the time, everybody would pay back their loan who we don't have information about, while in the low state of the world, we assume that those people would default. We implemented with a gradient booster tree on 500 predictors. We also have some comparable work with neural networks, but turns out that for us, the gradient booster trees do slightly better. And then we build a prediction function for credit call default, where we use a custom loss function to model 3 different cases. So the first case is a lender who minimizes average prediction loss across all states of the world. So mixing the high state with 80% weight and a low state with 20% weight. A regulator who minimizes prediction loss in the bad state. And let me just show how different those 2 functions look like. So those are the graphs I will show you for the next few minutes in order to compare different policy outcomes. On the x-axis, we have the utility in the high state of the economy. So it's the mean squared error if the state of the economy is good. And on the y-axis, we have the mean squared error in the low state of the world. And here I'm plotting basically the Pareto frontiers between those 2 for different ways of choosing the function. So for example, the one on the bottom left and on the left, which is the test in the out of sample data, would be would be a simple linear model. So this is a linear regression model with just 5 regressors. And so the regulator here among those functions would choose one that is as far up as possible, because the regulator only cares about low state utility, while the lender cares about average utility, which is a combination, an 80-20 combination of a high state and low state utility, and ends up in a point towards the right. And so the first thing we see here is that as we make the model more complex, so we go from a simple linear model to a complex linear model using all variables, or going to an even more complex boosting model, we see that both in sample on the right and out of sample on the left, that these models can perform better both in terms of the low state and their high state utility. And so that motivates kind of why we're interested in looking at those more complex models. So in principle, those more complex models have the benefit that they could do better, in this case, not just in terms of average performance, but also performance across states. But now, of course, the question is, how much of that benefit can we actually realize if the regulator cares about low state utility only and the lender cares about both, and these models are too complex to fully regulate? And so that's what I now want to show you to basically provide some empirical evidence for my claims in the theoretical example. So specifically, I'm now assuming as a third option that there is a lender who still minimizes average prediction loss, which is their preference, but subject to a constraint that the simple description of their function agrees with what the regulator would want the lender to do. And specifically, we're using here linear proxy models, meaning we're just assuming that the explanation is a linear regression on 5 predetermined variables, where we determine these variables in 2 different ways. Either we choose the 5 variables that are the best at explaining the overall variation in the outcome. So think of this as running a lasso on repayment on all the axes. Or we use a targeted explainer where we specifically ask what are the variables that are most related to those cases where the regulator and the lender disagree over. So in this case, think of this as a lasso of missing data on the set the X covariates. So what do we see?
Jan, you should wrap up in the next minutes. Okay.
Okay, great. So let me wrap up by showing you those empirical results. So what we see is that if we use those complex models, this is where regulator and lender would end up. If instead we restrict to a simple model, we would get substantial loss in our utility, even if we ended up on a regulator point here. While if we use a complexity constraint, we can constrain the lender to choose from this much smaller choice set and blue, in which case we can improve both using the agnostic and the target explainer in this case over the regulator's outcome if we restrict to simple models. All right, so let me just go to my conclusion here. So I started with an opportunity and a challenge, which is that as we use more and more automated rules to take high stakes decisions, then the fact that these are automated allows us to systematically scrutinize them, because we're now using algorithms that can in principle be described mathematically. However, at the same time, there's a challenge because these algorithms are often so complex, then we cannot fully explain them, which asks the question how we should optimally restrict and explain them. And in this project, we model this trade-off in a principal-agent model. And we give the answer that there is a complexity oversight trade-off here that is best responded to by using explanations that are targeted to the specific source of misalignment. And we then calibrate this in data. I just showed you a risk example. We also have a disparate impact example in our paper that shows that in those cases, the excess cost of full transparency outweighs the cost in terms of misalignment, and we're generally better off by allowing for complex models and explaining them in a simple way. Okay, this is related to a broader agenda, so if you're interested in that at all, I'm happy to send you an updated version of our working paper. Feel free to send me an email. All right, thanks a lot.
Thanks so much, Jan. Can you take over, Paul, please? You should be able to share your slides.
Yeah, and let me unmute myself so you can hear me. Okay, thanks so much. Thanks a lot, Jan, and thank you to the organizers, Maryam and the organizers, for inviting me to discuss this. I'm embarrassed in that I had seen an much older version of this ages ago, and it speaks to the impact that having young children has on your ability to remember the paper. I was like thanked in the acknowledgements, and I remembered then that I had read it once, but it actually has changed significantly, and I got to spend a lot more time thinking about it. So I'm hoping that kind of what I'm going to do today, as you could see from Jan's presentation, there's kind of a lot in the paper. And what I wanted to do, there's a certain irony to a person who works in econometrics and empirical work to be giving some theory overview on this. But I thought it would be helpful because considering kind of the audience and thinking about this in here, there's probably a mix in terms of this. And, you know, what is the paper about? There's probably a broad range of them. And I think Jan started actually from kind of the finance and algorithmic part of it. And then ended kind of talking about the mechanism design. But certainly if you think about the theory aspect of it, this is mechanism design, or this is, you know, a principal agent problem. So I was thinking back to my contract theory and corporate finance classes back in graduate school. And, you know, you can kind of think about this is the point, is that this paper is trying to think about a problem in which there's a principal and an agent, in which, you know, there's some kind of private information for the agent, and then there's misaligned preferences between the principal and the agent. So, you know, this is Bank's original kind of paper thinking about this setting. And, you know, the whole intuition of what we think about in these settings is that there's just trade-offs. There's these misaligned incentives, which are bad for the principal. And then there's this private information that's good for the principal in the sense that we want the agent to be acting on it. We kind of want to let them do what they're going to do because they're going to do a better job than us. And so, you know, much of this literature, and I just want to touch on this because this is gonna be relevant for some of the comments in the kind of broader space, thinks about the incentive contracts given to the agent. So when we take contract theory, you know, a big part of what we're thinking about is, okay, how do we think about optimal contracts in different types of games such that we can induce effort on the part of these agents that is going to reflect kind of what we want. Effort in these games is typically noisily observed, and that creates these kinds of problems in terms of what's verifiable and what's not. Kind of what's relevant, and this is where things kind of went off, they were no longer on my syllabus from my graduate classes, in the sense that it actually turns out, so this is papers in a class of what gets called delegation models, where kind of it's not thinking so much about the contract per se, in the sense that we're not trying to sort of think about payments or how to structure payments in order to induce a certain, to align incentives, but rather we're saying, look, because of legal or other legal issues or something else, we need someone else to take care of something for us. They are going to act differently from us. So a nice example of this is like, you have a school, there are teachers, the teachers have to give grades. The grades that the teachers give, we know that the teachers are going to do a better job than us, but at the same time, we know that the teachers might inflate the grades of their students, for example, because they really like their students. And so we kind of impose some restrictions on them. So that's like kind of a classic example in this setting. And really kind of the key point here is that we're not thinking about the contract per se or the mechanism to design it. Instead, we're going to put restrictions on the agent's action space. And so kind of the canonical example that shows up in the Holmstrom 1984 example that isn't talked about in here is, we're a regulator dealing with like a monopolist and we want to set price caps. So there's prices, the monopolist is going to set prices. And so we want to worry about like, okay, we don't want them to set the price too high because then we know they're kind of exploiting rents, but we want to allow them some discretion. And so this is useful, I think, because it sort of helps clarify kind of what is the type of problem that we're thinking about in this paper, which is, shut down a few channels that we might think of as being relevant, like, for example, transfers or something else in which we want to pay or penalize someone. And then second, it kind of puts in the literature of, once I went back and was reading these papers, I was like, wow, this stuff is all very complicated. And when I talked to my theory colleagues, sort of the delegation literature is a bit of a mess, basically in the sense that it's very challenging to solve this stuff in a general sense because just because it makes the problem that much more complicated when you can't do transfers. Basically, if you want to allow things to be general and you want to have multiple actions, things become quite complicated in a general sense. So a lot of the literature existing here, so this paper here, this Alonso and Matuszek paper that that Jann cited, they're actually focusing a lot on a one-dimensional decision like price. There's this Alex Frankel paper, which actually Jann's job market paper kind of references and thinks about a little bit. That's thinking about multiple and has these other pieces that are kind of interesting. But it is true that the canonical case is one dimension, and so this paper is kind of right at the frontier in this, which makes it very challenging in some ways. So I just want to flag that think of this as it's trying to do a very hard mechanism design problem. And so then I think we have to kind of think about, well, what is the best possible way in which you can do this, and kind of what are we doing in here? So simple delegation problem where what's happening is, what do we say? Okay, well, the issue is in this paper, there's some conditional expectation. So like the true conditional expectation, where basically what's going to happen is we have some outcome. So default is a good one, or repayment based on some characteristics. That's a conditional mean function. So that's like that's some potentially, if we haven't realized what X is, that's a random variable, and it may vary based off of information. And then we're thinking about the agent's prediction of that conditional mean function. What I struggle, so like what's a little bit important here is, because we're thinking about this as a delegation problem, or generally is this principal agent thing, is that it's a little bit hard to think about, and I struggled a little bit in the empirical examples, is, a lot of the times it's pretty concrete of like, what is the thing that the agent has that is an advantage over the principal? And like in the case that that Jann gave in the talk today, I think it's a little less clear, right? Because to some extent, actually, it's not so much about a value of the signal; it's just a totally non-aligned preferences, which then it's fine. There's this distortion, but then I guess the question is, why doesn't the principal just tell exactly what the function is if you kind of have data? So there's some element of data that's there that is private, but it's not totally obvious where that's coming from. So I struggled a little bit with that. I think it's like there's some element here that once you start putting it in this problem, you're like, okay, well then what I need is this, we can misalign incentives, great. And typically we need some kind of hidden action problem. And it's not obvious notationally where that happens from. Like in the credit score example, I was thinking about this, like, do we think that what's happening is it's like private information, or is it the like state of the world, which is, state of the world is the example, but then why can't you just have state contingent contracts in which you kind of think about that? And the reason why it's important is like, you need to know where the private information interacts with the X's. So it was a little hard. You didn't get to see it super fast, but in that linear regression with multiple characteristics, some of the characteristics varied with the state of the world and some of them didn't. And to be able to, you need to target those characteristics. That's where the distortions occur. And so we really want a concrete mapping that says, well, this is why private information interacts with this thing. And like, what are the types of things? So that's, if you want to do targeted explainers, that's the thing you got to target. And so there was a little bit, I got lost a little bit on thinking about what is private, where do the distortions occur, and where do the targeted explainers happen? Because as soon as you get in a world in which you're thinking about a delegation approach, it seems like it should be obvious where the private information is. So like, in the finance setting, if you made it only about finance, I think like there's an obvious version of this, right? Where banks used to just be banks and be in, Topeka, Kansas, there's private information that can't be verified. We know this person and we're going to just make them loans. That's soft information. That used to be a thing. And it's like hard to verify that. Maybe now you live in a world where there's private data, but then you wonder why the regulator can't kind of get access to that. And then the third one, which I kind of thought maybe was what had in mind, is like the regulator moves super slow. And so we kind of just have these ideas and we're like, look, you can kind of respond nimbly to this and we'll ex post kind of follow up with it. But then I didn't understand why the principal couldn't kind of construct some state contingent things. And so I struggled a little bit with understanding this. And that the reason I say this is like the auditing thing makes a lot of sense, but it clearly requires a very tight linkage between what is the private signal and the kind of the underlying piece. And so, you know, the paper talks about this a little bit. You can think about this like as a version of multitasking, where you're thinking about the weights you put on these different characteristics. And the complexity is that you can't really observe all the tasks at the same time. And so then I wonder kind of, is there a way of a literature kind of thinks about combinations of this? That feels a little bit like what's going on there. Let me speed up a little bit. So this is a comment I've said before, and I think I still feel this comment relatively strongly. So I want to understand a little bit of like what makes it specific about algorithms. So for example, I could imagine f of x being Paul Goldsmith-Pinkham, and Paul takes in a bunch of characteristics. He has to make decisions. He has a bunch of things he observes. In models where we do this, we assume that people are kind of deterministic. There's not this random piece there. And so we can audit people too. Like there's this example, think about economists doing the job market process. We take lots of inputs and we rank them. It's kind of hard to understand what's going on. I still don't fully, I know in the literature that there's an algorithmic evaluation literature in CS and in econ. And so it's obviously important, but then I sort of wonder, is it more that we're kind of saying things about decision-making more generally and that this is a useful way to think about it? Is there something special to algorithms in this? And so that I think would be very helpful to understand because, and maybe it's about transportability or something else, or maybe it's about the function restriction, which is what we've historically done. It would be helpful to kind of make that exact, because if we want to make it just about algorithms, that's kind of relevant. One thing on the theory, as Lisa, I understand it, is like, because like I said, it's like a super hard theoretical problem. Solving this with general utilities, I think, is quite hard. A lot of the stuff is focused on quadratic laws. And my understanding is like, that's a function of kind of what needs to exist in this literature. It's like hard to do anything without quadratic utility in this, which is fine. But I think we want to be kind of careful in terms of, this broad space of mechanism design that applies in a lot of places. I think Jann didn't get a chance to put, I think this picture is like amazing, which is, I always thought it was like, if I like really understood what was going on, it's like, there's this thing, we want to kind of understand what's going on. I really think this auditing piece of this targeted auditing is really something kind of novel and unique, because a lot of the auditing literature in the theory space, I think, has focused on the outcomes, which is making risk exist for the agents, whereas this is really about targeting like the actual decision-making process itself. And, I think the challenge is like in the mechanism design literature, it's unclear. I think there's we have to think a little bit harder about the game for a given example. Let me just kind of quickly say this thing, because I think this is a little funny, and I maybe just like will give some broad perspective. Like two things. One, knowing what the policymaker wants is a little hard. Like it's not obvious to me that the CFPB or the Fed knows what they want, which is like there's a lot of uncertainty. Like regulatory uncertainty is a big component for the agent. Just to give you an example, like the stress tests, it's pretty well targeted. In that case, it's pretty well targeted, but like the CFPB, it's not obvious, do they care about, which piece do they care about? Are they caring about disparate impact or something else? And maybe the agent kind of doesn't really know. One thing I wanted to just comment is this line in the paper: we can restrict algorithms to produce prediction functions that are simple to be transparent, like a 10 variable logit. And I thought this is not Jann's fault. Like we say the same thing about a simple model versus, but I'll tell you, when you try, like I worked on the stress test modeling team at the Fed, and nobody understands what a 10 variable logit is. I mean, you think about what a logit is, right? Like really what we think is easy to understand is a linear regression. Once you do a logit, it's like, oh, well, where do you evaluate it? People are doing evaluative trainers even with when you're not doing neural nets. Like I think there's actually something useful to, like this point about explainers, you don't have to be in an XGBoost world to have this work. And so I actually think low dimensional representations of things is actually maybe just like a general point that is an interesting thing to think about, independent of the algorithms. And maybe algorithms are like a great example that ties in there. It's just like, just back to this, different objectives, things like, right, like Jann didn't get to show the disparate impacts, but there's two things and you have these trade-offs. And it's like, all right, well, in principle, in reality, does the principal know or commit to a single objective? It's like, probably not. And then it's kind of interesting to think about, okay, well, that's uncertainty in this. Like maybe there's risk that's there. Like, for example, do we really see many banks using neural nets? Actually, it turns out, this recent MBR working paper, FinTech lending with low-tech pricing. Like basically, FinTechs are kind of all using conventional credit scores. They're not doing anything complicated. That's probably because they don't want to get killed by any regulator. And so that's interesting to think about and maybe beyond the scope of this paper. But there is this interesting, so there's this paper by my colleague Florian Ederer and some co-authors on like strategic opacity and how that like creates incentives that aren't necessarily first best, but then create other kind of benefits by kind of being opaque in the way that you act. So that's probably unfair in the sense that it's beyond the scope of this paper, but it does kind of get, I think, a little bit closer to the reality of it. So let me stop there and give back control.
All right, guys, thanks so much. It was so interesting. I'm so sad that the talk and discussion are so short. I wish it was like 2 hours and then we could have them like sit and discuss everything. So everybody, to all the audience and the panelists, if you have a question, please raise your hand and I will call on you. But to start with, I'm gonna abuse my my position to ask the first question, which is actually a couple of questions. So Jann, just feel free to answer whichever of them that is that you find fit. So the first one is very related to what Paul mentioned, that I was thinking about what is the exact restriction that you need between what the objectives are, what is it that is it an information difference? Is it an action difference or what? And like a little more specifically, maybe basically in a sense, let's take a very simple example that Paul mentioned, which was basically we are trying to hire very good students as like our new colleagues. So there is a target. The target is to be hired, okay? Now, like, we want to hire the best student. Each student want to say that it's the best. So there is a difference in utility, but it's kind of easier if you want to do like a quadratic, there is a target, and then they send maybe signals, and we can process only as much of a signal, okay? So this would be something which would be, and what we are doing, we are saying, okay, you write a job market paper, you do things. So that's really bringing it down to a low dimensional space, okay? But we have, in a sense, chosen what are the spaces, dimensions of the space that we want. So this seems to me a little like what you were saying, but I was not sure if this is exactly that, or you have like something broader in mind, or this is it, or let me stop here, because otherwise I'm gonna go the whole 10 minutes.
Yeah, great. Let me maybe start with that first point, also mirroring, I think, one of Paul's main points, which was about what is the exact source of, in this case, difference in information between the two. And so actually the view I have is that in many practical cases, I would think of it as basically having access to two different technologies, meaning that it's the agent or the lender in this case who's actually able to run a complex algorithm, while the regulator may not necessarily have the technology to do so. Or, you basically have one complex machine, the machine effectively solves some loss minimization problem for you, but you may not be able, as the supervisor of that machine, to fully do that yourself. And so you rely on a simple description to understand it. So I would, my proposal here, so I do agree that in our formal modeling, it's kind of the weak point in that we are not very clear about why can't a principal just solve that problem herself. And I do think it's a very realistic thing in the sense that the regulator would not solve the full credit scoring model as well as the lender does. But now the challenge is kind of, why is that the case, right? And in my eyes, we could motivate that simply by saying they have different technologies. So the lender has access to the technology to do so, while the regulator would not have that technology. I think that would be my quick answer to that. So you're basically now asking about an example where you say, maybe we want to evaluate something complex in a complex way, but we only we want to build a simplified projection of it. I do agree with that example. The one thing I would add here is that I think our model is really about saying not what is the optimal way of describing the original job market applicant, but assume now you're taking the view of you are the university and you want to say audit whether the way that the economics department has done their hiring this year was compliant with what the process should be. Then I think my argument here, to summarize kind of the structure of the argument, would be rather than saying we should therefore ask what was in the applicant file that is most helpful for us to decide whether to hire somebody or not, we should ask what is in the file that is both informative about whether we should hire or not, but also most likely to be something that we disagree with relative to the economics department. Because if we only look at kind of the first order information in the applicant file and whether we should therefore hire them, we may not put enough emphasis on the aspects on which we potentially disagree, because maybe the main reasons for hiring or not hiring is actually not what we disagree with the economics department, but maybe we are more worried about the economics department using certain specific things in a way that we don't agree with in terms of policy. I'm not sure whether that responds, Maryam, to your second part of your question.
So my second question was a lot simpler than this. So you even in a sense, complicated it more. I was thinking just the two people. So let's say us and econ department are the same. Okay. Yeah. So and the agents are the students. Okay. So they are the ones who are trying to, I don't want to say even trick us. Okay. They're the ones who are trying to send us any signal which is more aligned with the buckets that we have decided. But so one in this example that I made, for instance, one bucket that we can choose is the one that is hardest for them to replicate. That's the simple. That's something about the very, very basic, simple, old, moral hazard problems. Okay.
Right. So I think in this case, our model would be more about saying, what are the aspects of the submission that you want to audit specifically because you're worried that you have misalignment over that part, while maybe you're not really worried about auditing the parts that are, hard to manipulate, but you may say, oh, therefore I should focus specifically on those things that are easier to manipulate because they are most likely those that would be different if I don't put any constraints. So I think that in that example, that would be how I would see the connection. But I like the example, and I think also like the idea of kind of trying to break it down to kind of a simple.
So that's basically what I'm. So as you said, you said it the best possible way. That okay, maybe we can separate out what's hard to manipulate, what's more important, what differentiates more, and can you use your framework to think about which one is more important to put in your load, to put into the load dimensions that you want to choose.
All right, that's super helpful. I do think that's a great point, and I think it's something we should think about for the paper. Yeah. That's
really interesting. Okay, sorry guys. So I took all the point, but it's fine because there were no questions from the audience. So let me just say thanks. So we're gonna now switch off the recording, and we're gonna upgrade all the attendees to panelists so that we can all openly discuss things. And for everybody who won't be able to join us in the open discussion, we are looking forward to seeing you in our next webinar on May 29th. Thanks so much for joining us.